smallest thing in the universe. Well, if we zoom into a nucleus and down into a proton, we encounter something truly tiny. Quarks. But what's more amazing than their size is the fact that they could hold the theory that explains why the entire universe is the way it is. Let's dive deeper to know how. According to the standard model of physics, quarks are elementary particles, just like electrons, photons, and gluons. To give you a sense of scale, a quark is thought to be less than 10 quadrillionths the width of one of your hairs, which is too small to be seen even with the most powerful microscope. So, you say, if they're so small that we can't even see them, how can we understand the nature of these elementary particles? With Paul Dirac's quantum field theory, of course. This theory says that the universe is composed of fields, or a set of values assigned to every location in space and time, like coordinate fields but with different values. Elementary particles are defined as energy that warps their respective field, in a shape that looks much like a ripple in water. This energy is what defines the particle's mass, as defined by Einstein's most famous equation, energy equals mass times speed of light squared. Interactions between fields can be described like elementary particle tuning forks, where the vibrations of one tuning fork interact with another tuning fork, similar to the fields. These simulated interactions are what we use to understand the forces of the universe. There's just one problem. This theory can't define how one of the forces, gravity, works on a quantum scale, since a gravity field doesn't work. You see, we need stationary fields acting like a stage for us to concentrate on particle interactions. A theoretical gravity field, being influenced by all objects at once, is more like the surface of a bouncy castle being trampled by the feet of 100 kids, making it impossible to understand where a particle would be, and blowing up once concise QFT equations with incalculable infinities. However, we can't just hide quantum gravity under the rug. Quantum gravity becomes extremely important when we think about the things that break QFT with infinite densities, like black holes or the very beginning of the Big Bang. We need to understand these events in order to understand our universe. However, we can try to define quantum gravity with string theory, a notion that redefines elementary particles as having thin strings of energy inside of them, which vibrate at different frequencies for different particles. In this case, we define gravity as a new elementary particle, the gravitron, which suggests that gravity is made out of the same stuff as other elementary particles and can come under the laws of quantum mechanics, uniting with general relativity and creating a theory that fundamentally defines what has never been defined before. Although string theory isn't perfect, efforts are still being made to test other aspects of string theory. As of late, researchers are trying to prove the existence of superpartners in colliders like the LHC. The discovery of such particles is an important step in proving a crucial part of string theory, supersymmetry. This allows the equations to simplify. Research is also being conducted on how we can test for the vibrations of tiny strings in space, or explore superpartners that require even higher energies than current colliders can provide. Any way you look at it, string theory holds some intriguing possibilities, and who knows, maybe it will be the super elusive theory of everything.